Did you guys come up with an answer for this one yet? Okay, so the ideal value, or the desired value, is found by doing what? We add them together and divide by 2, which gives us 1.250, correct? That's our desired value. To find our allowance, but once we have the desired value, we can just take that and subtract one of the endpoints. Or we can subtract the endpoints and divide that by 2 to get 0.005 inches. So what this is currently 1.250 inches plus or minus 0.005 inches. But that is an absolute allowance. And I requested a relative allowance. So how do we change that into a relative allowance? Well, relative allowance is a percent. So it's out of 100. So I need to know 0.005, how much that is out of 1.25. So we will cross multiply and divide. 100 times 0.005 divided by 1.25 is 0.4. So that's 0.4%. So that's saying is this is really 1.250 inches plus or minus 0.4%. Did everybody get that?
Why do you divide by 0.5 instead of 0.005?
100 times 0.005 is 0.5. Then divided by 1.25. Did anybody actually get the 0.4? Any questions on where it comes from? Does it make more sense now? Sort of. All it was finding a percent, so I had to put the percent over 100, so blank over 100 equals my 0.005 over 1.25. Then it's cross multiply and divide to solve the proportion. Okay, well, what we're going to look at today, for those of you in automotive, this should be a little bit of a review. Resistor color code. The colors are black, brown, red, orange, yellow, green, blue, violet, gray, white, gold, silver, and none. Each of these has a numerical value to it. Black represents 0. Brown represents 1. Red represents the number 2. Orange would be 3. Yellow 4. And green represents 5. Blue is 6. Violet 7. Gray is 8. White is 9. Bless you. So those are the numbers they represent if they're in one of the first two bands. If they're in the third band, bless you again. If they're in the third band, All those labeled in brown represented the numbers that they represent there, except it's 10 to the power of that number. Gold would represent times 0.1. Silver would represent times 0.01. Technically what it is a -1 and a -2, but we'll see what that means in just a little bit. In the fourth band, sometimes referred to as the tolerance band, black is plus or minus 20%. Brown is plus or minus 1%. Red is plus or minus 2%. Then we jump all the way down to gold, which is plus or minus 5%. Silver is plus or minus 10%. And if there is no tolerance band, it's plus or minus 20%. So let's take a look at a resistor here. Let's say this first band is brown, then green, red, and silver. Notice I've got it separated out. The first two bands, then the third, and then the fourth. So in the first two bands, brown is what number? 1. Green is what number? 5. Now the third band is a power of 10. So it's 10 to the power of, red stands for 2. So it's 10 to the power of 2. So what that is, 15 times 10 to the power of 2, or 1500. The other thing you can do is you just say the 2 is the number of zeros you got to put at the end of your number. Of course, that unit is ohms. And what does silver stand for? Plus or minus 10%. So that is a plus or minus 10% for a relative allowance. Let's look at another one. By the way, that color code is on page 200 in your book if you didn't want to write it down. Let's say we have gray, red, yellow. What does gray stand for? Red, 2, and yellow, 4. So it's 10 to the 4th, or 4 zeros. So it's 82 followed by 4 zeros. 820,000 ohms. What's the plus or minus? There was no band given here, was there? So that's going to be 20. When there is no tolerance band, it's plus or minus 20%. 820,000 ohms. Yeah, I mean, it's not uncommon to have a 25,000 ohm. Most ohms are kilo ohm, or most resistors are at least a kilo ohm, or just 1,000 ohms. You can. Gold is 5%. It's on page 200 in your book. Okay. So let's say we have orange, blue, gold, gold. What's orange stand for? 3. Blue, 6. Gold, in the third band, if it's in the fourth band, it's plus or minus 5%. But if it's in the third band, it's plus 0.1. Multiplied by 0.1, or times 0.1, you're right. I said plus, didn't I? That should be times 0.1. So 36 times 0.1 is 3.6. Then plus or minus gold would be 5%. In your notes, read this one for me. Violet, orange, red, silver. So violet stands for 7, orange, 3 red, 10 to the 2, right? So it's 7,300 ohms plus or minus 10%. Now, of course, you recognize this as a relative allowance or relative tolerance, if you call it that. If I wanted to change it into an absolute allowance, I have to find what 10% of that is. So 10% is 10 out of 100. I'd find how much is that out of 7,300. If I cross multiply and divide there, I get 730. So as an absolute allowance, that's 7,300 ohms plus or minus 730 ohms.
How do you get the power you said red was 10 to the second?
Red is 2, right?
Yeah.
So that's 10 to the 2.
So you add.
It's 10 to whatever the color, whatever number that color represents. So that's just saying if it's red, that means 2. That adds 2 zeros to the end of the number. So for this one, let's say I have blue, green, orange, and we'll go gold. Blue is 6, green is 5. Orange is 3, it's 10 to the 3rd. So it's 65 with 3 zeros after it, so 65,000. So the orange is 3, that means I add 3 zeros to the end. And then, of course, gold is plus or minus 5%. Now, if I want to turn that again into an absolute allowance, I have to find 5%. So 5 over 100 is 5%. Need to find how much that is out of 65,000. If I cross multiply and divide, 65,000 times 5 divided by 100 is 3,250. So that is an absolute allowance, 65,000 ohms plus or minus 3,250 ohms. So I'm going to have you guys try one. Red, green, brown. And black is the 4th band. Give me the absolute allowance for that. So red is 2, green is 5, brown is 1. So it's times 10 to the first. That's 250 ohms. Black is plus or minus, careful, 20. None is also plus or minus 20%, but in some cases the black also stands for it. So then we have to find 20%. 20 out of 100 equals blank over 250. We cross multiply, divide. We get 50. So that's 250 ohms plus or minus 50 ohms. Now, of course, that implies a range. If I had 250 ohms minus 50 ohms, gives me a lower end of 200 ohms, up to 250 ohms plus 50 ohms, gives me an upper end of 300 ohms. So I have that range. So let's say I have blue, orange, gold, silver. What's blue stand for? 6, right? Orange is 3. Gold is times 0.1. So that's 63 times 0.1 or 6.3 ohms. Silver is plus or minus 10%. So we find the 10%. 10% is 10 out of 100. How much is that out of 6.3? To cross multiply and divide, we get 0.63. So that means this is 6.3 ohms plus or minus 0.63 ohms as an absolute allowance. So that gives us a range, 6.3 minus 0.63 of 5.67 to 6.3 plus 0.63, 6.93. There's our range. So in your notes, if I give you white, green, red, and gold, find the range. Okay, so white is 9, green 5, red 2, so that's 9,500. Plus or minus gold is 5%. So we go to find 5% of 9,500. We cross multiply and divide, we get 475. So this is 9,500 ohms plus or minus 475 ohms. So 9,500 minus 475 is 9,025. Up to 9,500 plus 475 is 9,975. Cool. Any questions on those? We'll start working backwards. What if I give you that a resistor is 38,000 ohms plus or minus 10%. Well, when we go to code it, it's got to be a 3, an 8, and then the third digit is the number of zeros. There are 3 zeros. 3, and then we'll do the tolerance band later. So that first band is represented by a 3, which is orange. Then the 8 is gray. And then 3 is orange again. Then my tolerance band for plus or minus 10% is silver. What do you think? Not terrible? So if I give you 4,700 ohms plus or minus 5%, code that for me quick.
Where are these lower resistors on automobile cars and trucks and stuff?
Guys, want to help them out? The resistor.
I mean, where, like, they're not in the fuse plug or nothing, or they just like, lower motors.
Yeah. Anywhere you need any sort of a voltage reduction. So a lot of, because you have a 12, it's actually a 13.6 volt system, but a lot of your smaller motors, only like a 4 volt or whatever, use resistors to reduce them. Bridge circuits to control voltages and stuff like that. Your dimmer switches and stuff like that, those are usually a bridge circuit. Or sometimes they're what they call a pot, a potential variable resistor. So it changes the resistance, it changes the voltage across, it changes the current. Okay, so here, the first number is going to be a 4, which is yellow. Then it's 7, which is violet. Viking colors. And then 2 for 2 zeros, which is red. And then tolerance, gold. Any questions on those? What if I tell you that our resistor is 32,000 ohms plus or minus 6,400 ohms? What would we have to do first before we could code that? We would have to turn it into a percent. It's an absolute allowance. Now we'd have to turn it into a relative allowance. So we put the allowance, the 6,400, over our desired value, 32,000. And we cross multiply and divide. 100 times 6,400 divided by 32,000 is 20. So that's a plus or minus 20% resistor. So if we code that, it's 3, which is orange. 2 is red. 3 zeros, which is orange. And then I can either leave it blank or I can put in black for the plus or minus 20%. I believe your textbook uses black for plus or minus 20%. Most of the time I've seen it just left with no tolerance band for plus or minus 20%. Or we can go one step further. I can give you that the range is Oh, let's see here. $52,200 ohms to 63,800 ohms. This goes back to what we did at that warm-up problem at the beginning of class. Turn that into a desired value and an allowance. Find the relative allowance and then color code it. I'll give you a couple minutes. So to find the desired value, we add them together. Divide by 2. So we add them together, we get 116 divided by 2 is 58,000 ohms. That's our desired value. To get our allowance, we could just take that and subtract one of the others, or we could subtract them from each other. And divide by 2, it's going to give us 5,800. What's that? Good. To find then the relative allowance, the percent, you can probably find it without having to set it up, but we'll set up the proportion here. 5,800 over 58,000. Cross, multiply, and divide, you get 10%. So this is 58,000 ohms plus or minus 10%. So we would color code a 5, which is green, an 8, which is gray, 1,000 has 3 zeros, that's orange, and 10% is silver. Now, many of you have probably never seen, and I didn't use any examples here either, where I had red or brown tolerance bands. Red is plus or minus 2%, brown's plus or minus 1%. Those are basically military grade resistors. You hear about, the military spending like $5,000 for a hammer or stuff like that, or $2,000 for a bolt. The reason for that, let's say a standard bolt and nut. A couple days ago we talked about that idea of a clearance fit. That bolt, when it goes on the nut, has to have clearance. Or the nuts, I should say, when it goes on the bolt, has to have clearance. So usually there's a couple thousandths of an inch of clearance, so that nut has room to turn. You can turn it on with your fingers onto that bolt. In fact, usually it's more than a couple thousandths clearance. The problem is that clearance, when that nut is on the bolt, if it's on something that vibrates a lot, what does it do to that nut? It vibrates it loose. It kind of starts to turn as it vibrates. Because the reason it does that is because when that nut's on the bolt, there's room between the nut and the bolt, so that nut can literally move back and forth on that bolt a little bit. And that little bit of movement causes it to vibrate loose. So we're looking at military grade equipment. You can barely get that nut started on that bolt. There's no way you're going to hand tighten it at all, because the tolerances are so tight. That nut is almost no clearance on that bolt. It goes on there that tight, so you need a fairly large handled wrench just to turn it down for it's snug, because it binds on that bolt so much. And that's exactly for that reason, is there's no room for it to vibrate as that equipment moves and runs and vibrates. So the chances of it vibrating loose are very, very low.
I have a friend that does avionics technician. He was telling me about this stuff. Like,
Yeah.
I take working on a truck over the helicopter and stuff. I work on
Yep. Yeah.
Otherwise, that, like, you can't even hand tighten a bolt. They're that. Like,
Yep.
what happens
They
if you
have.
cross thread? Like, you get fired.
Yeah, you cross, those bolts are expensive. And just like the resistors, you know, to get a 1 or a 2% resistor, there is no special process for creating those. What they do is they actually create, let's say they create 1,000 resistors. They're going to test them. They're going to run them through a tester. If they're within 20%, they throw them in the 20% bin. If they're within 10%, they throw them in the 10% bin to go get a silver stripe on them. If they're within 5%, they go in the 5% bin to go get the gold stripe. If they're within 2% or 1%, they go in the red or the brown bin. Well, if the military orders resistors have 1% allowance, out of that 1,000, they might get 10 of them that are good, that meet that 1%. So when the military buys those 10 resistors, they have to pay for all 1,000 that had to be produced. Same with these bolts. They may have to produce 50 bolts in order to get one that meets those tolerances, or more. There might be 100 bolts, who knows? The military pays for all of them. In fact, most companies that do military contracts lose money on the military contract. So I ask, well, how do they stay in business and how do they turn a profit? Well, it's actually simpler than that even. Of these 1,000 resistors, 10 of them met the military specs. They sold them to the military. They took a loss on them, but they still have 990 surplus resistors. They're still high quality, just not high enough quality for the military. So they sell off those surplus resistors, and that's where they make their profit.
Why don't they just use nylon in the bolts?
Those eventually would wear out in the vibration. That nylon would not last very long. Even like lock washers and stuff like that wouldn't hold for very long.
I'll try to find it. I'll have my friend try to send me a video. They were, I don't know if he can or not, but he
That's
sent me
classified.
he sent me a video when they replaced the rotor on one of the Blackhawks.
Yep.
And they started it up and it started wiggling real bad. So he's like, oh, I'll just go tighten a little bit. He went to tighten it. They went to take off and the back blade flew off.
Yeah. Yeah, it doesn't take much the vibrations in those are tremendous. It doesn't take much clearance to make them come loose. Maybe not a lot of people realize that when talking about military contracts, that most companies lose money on the military contracts. They make their profit selling the leftovers, the surplus on the secondary market. In your textbook, page 203, there's exercise 4-8, 1 through 29, the odds.